Hi, my name is Sebastian Baum, and in this video I want to talk to you about Paleo-Detectors, a proposed technique for the direct detection of dark matter, as well as for neutrino-induced nuclear recoils. So let me start by reminding you of what the basic idea for the direct detection of dark matter is. So what we're looking for is some dark matter particle coming along, scattering with an atomic nucleus. There's two main challenges to this approach. A, the nuclear recoil imparted by the dark matter interactions is very small. Now, the other challenge is that these recoils are extremely rare. Otherwise, we would have long detected them. And in particular, the number of events is just proportional to the cross-section times the size of your detector times how long you measure. So we have not been successful at finding these type of recoils over the past decades. And obviously then what people have done is they've just built bigger and bigger detectors. So what we've been thinking about, though, is there a very different way to do this? And just look at this equation again. What I wrote down here, right, is that the exposure is the product of the detector size times the time you've been measuring. Now, of course, if you run a lab type experiment, you can only measure recoils for so many years. So what we've been realizing, though, is that there's a very different type of detector one can use. So the basic idea behind Paleo-Detectors are solid-state track detectors. What you're seeing in these pictures are damaged tracks imaged by different microscopes, imparted in regular natural crystals by an atomic ion traveling some distance through that material. And you can see this, especially these two pictures here on the left are taken something like 50 years ago. And you see here, this is with optical microscopy. You see these damaged tracks in here. Sorry, this is with optical microscopy. This is with transmission electron microscopy. You see these damaged tracks. You see these damaged tracks over here. So what's happening is that essentially as an atomic nucleus grinds to a halt via its interactions with the crystal lattice in that material, it locally messes up the crystal structure, which gives rise to a lasting damage track in the material. Now, as I said, these pictures on the left are taken by now almost 60 years ago. And the scale you can see here is this bar is something like a micron long. Here, this bar is something like 50 micron long. Now, on the right, you can see a picture that has been taken only 10 years ago or 15 years ago by now of damaged tracks. What you see here is actually the cross section of a track. And what I want you to note is the scale here is nanometers. So with modern microscopy techniques, in this example, transmission electron microscopy, we can get really high resolution and detailed images of these tracks. And it's much easier to detect them than with the microscopies or techniques 60 years ago. So that's the basic idea behind Paleo-Detectors. What I hope for that these pictures on the last slide have convinced you of is that those damaged tracks are real. In particular, in many natural minerals, once a nuclear recoil happens in such a mineral, you will impart a damaged track. In many minerals, once such a damaged track is created, it will be around for more or less forever. In many minerals, the time scale over which these damaged tracks disappear is many, many orders of magnitudes longer than 1 billion years. For example, in diamond, it's something like 10 to the 50 years. Furthermore, nature is an ample source of really old mineral. So Earth is something like 4.5 billion years old. It took Earth some time to cool down, become a nice place where minerals could just happily live their life. But many minerals routinely found on Earth are as old as 1 billion years. And as I also showed you on the last slide, modern technology now allows us to read out such damage tracks with quite astonishing precision. So that is the basic idea behind Paleo-Detectors. As the dark matter guy would come along, it would create a damage track in the material because it would give rise to nuclear recoil, and that nuclear recoil in the mineral would then create a damage track. And Earth has provided us with these fantastic detectors. They've been sitting around for 1 billion years, faithfully recording the events caused by dark matter interacting with them over 1 billion years. And all we have to do now is to get these minerals and look for the damage tracks, just image them and count how many dark matter interactions are recorded in these rocks. Why is this so powerful? I told you before that the exposure is the product of the size of your target times how long it has been recording damage tracks or events. Now imagine that you could read out the tracks in a 100-gram sample that's been recording tracks for a giga-year. If you want to match that exposure, a real-time lab experiment that you can operate for, say, 10 years, you would have to build a 10 kiloton scale experiment. The other advantage is that thanks to the modern technology, we can read out very, very short tracks. So you can imagine that the less energetic the nuclear recoil you induce is, the shorter the damage track it will give rise to is. And in particular, say you have a typical KeV recoil as would be induced by dark matter, the length of the corresponding damage track would be on the order of something like 10 to 100 nanometers. So if you have a microscope that can read out tracks with sort of nanometer scale length resolution, that would correspond to having order sub keV to keV recoil energy thresholds. So in essence, what a paleo-detector would be a recoil detector with exposures on the order of kiloton times years or 100 kiloton times years, but keV nuclear recoil energy threshold. Now, of course, if you run such a type of experiment, looking for damage tracks in a natural billion-year-old rocks, you might worry about all sorts of backgrounds, right? What are all the other things that could give rise to damage tracks or something that looks like the type of damage track that could be induced by a dark matter interaction? So first of all, you might worry about natural defects, right? We're proposing to use naturally grown minerals that have not been produced in any controlled lab environment, etc. Happily, natural defects do not look like 10 or 100 nanometer long tracks. They are either single site or they are much, much longer than the types of tracks we're looking for. So we don't have to worry about natural defects. You might worry about cosmic rays hitting your target, and either by interactions or directly from the charged cosmic ray inducing a damage track. Now, the way you would deal with cosmic rays in a paleo-detector is exactly the same as what you do in a conventional direct detection experiment. You would use a target sample that has been spending its life far deep, very deep below the surface of the Earth. One way how you could get such samples is from deep boreholes, because now we're not talking about operating a ton-scale experiment that you have to do in an accessible underground mine or some similar type of laboratory, but we're talking about getting some relatively small, maybe 100 grams or so of target material. And you could get this from something like pictured here. These are bore cores from ultra-deep boreholes, which people drill regularly to depth up to something like 10 kilometers. And if you could get such material from a depth of greater than something like 5 kilometers, backgrounds from cosmic rays would be essentially negligible. Another type of background you might, of course, worry about are radioactivity, right? Any naturally grown mineral will contain some trace amount of uranium, etc. Again, the way you would try to deal with radioactivity is similar to a conventional direct detection experiment. You would try to reduce the amount of radioactivity in your target material as much as possible by using radio pure samples. And luckily, Earth has provided us radio pure samples, although unfortunately now I don't have time to go into this in detail. Similarly, finally, there are neutrino-induced backgrounds, and there's not much you can do about this, right? There's no way we can shield neutrinos, so in the end, you just have to live with them. So what do? We've done a lot of careful studies of these backgrounds, and in the end, you just go and compute them. You try to reduce them as much as you can, and then you compute what the residual background spectra look like. And this is how a paleo-detector experiment looks in the mind of somebody like me, a theorist. So what I'm showing you here is the number of tracks per track length in log-spaced bins, going from something like 1 nanometer to a micron. Don't worry so much about the normalization here. That is just proportional to however large you choose your sample to be. What I want you to see, though, is here this white spectrum shows you the neutrino-induced nuclear recoil spectrum. And the pink band is the radiogenic neutron-induced backgrounds, and then there's this narrow background peak that comes from some particular radioactive decay. So at short track length, you have to live with, you're dominated by the by the neutrino-induced backgrounds. At longer tracks, you're dominated by neutron backgrounds, and then there's this little peak that comes in the middle. But look at how this type of diagram looks. It's a sort of LHC type, collider type diagram. where what you're looking for is you're predicting the shape of the backgrounds. And then you're looking for a slight bump over the shape of the backgrounds induced by some dark matter signal. And what I'm showing you here is an idea of a sort of relatively light 5 GeV-ish WIMP and a much heavier 500 GeV WIMP, right? And so what you would do is a collider type experiment where you look for a little bump, a little modification to this background induced spectrum induced by some WIMP, by some dark matter interactions. So once you've computed the background and the signal spectra, you can then go and you can crank the statistical machine and ask, what kind of sensitivity could I reach with the experiment like this? So what I'm showing you here is first an example of what we call the high resolution readout scenario. So this is something that could be achievable with, for example, helium ion beam microscopy readout, or maybe some version of transmission electron microscopy readout of small target samples, where we imagine you could achieve something like 1 nanometer resolution, track length resolution for on the order of a bulk sample of something like 10 milligrams. So this is the typical direct detection plane. This is the spin independent WIMP proton interaction cross section on the y-axis and the dark matter mass on the x-axis. In this gray band, I'm showing you the currently existing direct detection experiments. And just to guide the eye, this blue shape down here is the conventional xenon, the conventional neutrino floor in a xenon type experiment. And so this high resolution readout corresponds to having very low threshold energies. And what you see in these different colored bands are for different type of target materials, what is the reach you could get. And what you see is this is really aimed at sort of relatively light WIMPs below 10 GeV or so, where you can get sensitivity many, many orders of magnitude below current limits. You could run a different type of experiment, what we call the high exposure readout. So here you sacrifice some spatial resolution to get some larger sample, to get more exposure. So something like 50 nanometer resolution for 100 grams of material is something that we believe is achievable with hard X-ray microscopy that you would have to do at a synchrotron facility. And if we now again look at the sensitivity, what you see is it's not quite as sensitive as our high resolution scenario at low dark matter masses, but you can get sensitivity a few orders of magnitude below current limits at heavier WIMPs above something like 30 GeV. So in the beginning, I mentioned we could not only look for dark matter, but also for neutrinos, right? And what in particular, one interesting source of neutrinos are supernovae. So when a supernova goes off, it emits a lot of neutrinos, and these neutrinos can then on Earth induce nuclear recoils by their interactions with atomic nucleus. Now you have some sample that has been counting all the nuclear recoils over something like 1 billion years. And the cool thing you can do with this is you could measure how often do supernovae go off in our galaxy. What I'm showing you in this plot is as a function of the uranium concentration, remember uranium is one important background, in our samples, what is the smallest supernova rate we could detect? Here, these gray dashed lines show you a benchmark of what people believe the local supernova rate in our galaxy to be, a few per 100 years. And you could see if you could get a sample of something like epsomite, which is a relatively clean salt mineral, often found on Earth, of something like 0.01 parts per billion, which we think is a reasonable benchmark. You could measure the local supernova rate in our galaxy, and that would be the first direct measurement of the supernova rate in the Milky Way. But you could do something even cooler. Imagine you don't just look at one rock, but you look at a collection of rocks. One of them has been has been integrating for 100 mega years. The next one is 200 mega years old, etc. And now what you do is imagine you measure the integrated rate of whatever you're looking for in each of these. Now you can, of course, do a numerical derivative and ask, how does the rate change in between over this time span of however old your oldest rock is? One cool application you could do of this is you could ask, what is the cosmic ray rate on Earth? And the way you would measure this is you would look for the recoils induced by atmospheric neutrinos, which are caused by cosmic rays interacting with Earth's atmosphere, hitting your Paleo-Detector and causing some nuclear recoils within. Another idea, going back to dark matter, is to ask, could we also look for time-dependent signals caused by dark matter? Here the idea is, what if Earth over the course of the last billion years or so, has passed through some region in our galaxy where there's much more dark matter than happens to be around us today. And the examples that we looked at is either what you see in this picture is dark matter substructure from a simulation. So what if we pass through some dense subhalo? Or what you could also ask is, what if there's a dark disk formed by some dissipative component of dark matter? And if there is such a dark disk, then Earth would go through it every 30 mega years or so. So to summarize, the basic idea of Paleo-Detectors is to use the crystals nature has provided us with to learn about the nature of dark matter or our galactic history. Natural minerals have been recording information about nuclear recoils over timescales as long as 1 billion years, and we believe that with modern microscopy technology, it is possible to read out these nuclear damage tracks with an effective nuclear recoil energy thresholds on the order of keV. In this talk, I discussed a few applications of Paleo-Detectors that make me very excited. Amongst them, the search for dark matter and learning what makes up the missing matter of our universe, measuring the rate of supernova explosions or cosmic rays, learning about history, and I'm sure there's other options that we haven't even considered for the types of physics that one could go after with Paleo-Detectors. Thank you very much.